I want you to look at your textbook, page 718. Okay, page 718 is the determination of the reaction order from the integrated rate law. Okay, before this, okay, from what we have learned before, if we want to determine what is the order of the reaction, okay, we will run several series of the experiment that we change the concentrations of the reactants. Okay, and then we make calculation, we choose to experiment with the same concentration, and then we divide rate 2 to rate 1, then we will get what is the value of M and also the N, okay, the reaction order from the series of the experiment. So the graphical method, this is the second method to find what is the order of the reaction. Okay, this is a graphical method to determine what is the order of a reaction. Okay, and with this method, okay, we don't need to run several series of the experiment to get the rate. Okay, so if we look at to this integrated rate equation for the first order reaction, okay, if we rearrange back this equation, we will get ln A naught minus, ln A naught minus ln AT equal to T. Okay, if we look at to all components in this integrated equation for the first order reaction, okay, we observe that ln A naught will remain constant because A naught is the initial concentration. Okay, if we have a reaction, okay, initial concentration is 5 molar. Okay, this is the A naught. If I ask you what is the initial concentration now, then the answer will be 5 molar. Okay, after 10 seconds, I ask you what is the initial concentration of this reaction? The answer will still 5 molar because I asked you what is the initial concentration. But if the question is what is the current concentration of the reactant that is left, then it is changes with time. Okay, because the concentration of the reactant decreasing with time. So, of course, that the AT value, okay, the concentration at the T time will always change with the T. Okay, so ln A naught will always be constant. Okay, ln AT changes with the value of AT. Okay, and then K is the rate constant. So of course that K will be constant. But T is the time that is changes, okay, throughout the process, throughout the reaction. So that T change, K constant, ln AT change, ln A naught also change. So if we compare this, okay, to achieve the straight line equation y equal to mx plus c, okay, we can say that, okay, this k is like m, t is x, ln at is y, ln a naught is apa? C. Okay, so that when we rearrange back the equation, we make y equal to mx plus c, then we will get this equation. Ln AT is equal to negative KT ln A naught. Okay, so ln AT, this is your y, negative K is your M, the gradient of the straight line. Okay, and then T is the X, ln A naught is C. Okay, so if we plot a graph of the ln A versus T, okay, concentration of A, ln of the concentration of A versus T, then we will get a linear graph. Okay, ln versus time. Okay, with the gradient, look at to this linear graph. Okay, with the gradient of negative K. Okay, so if you look at, if you got a graph of ln concentration versus time, then it is linear. So you should know that the reaction is the first order reaction. As for the second order reaction, okay, this is our basic integrated rate equation. Okay, it is 1 over AT minus 1 over A naught equal to KT. It is the same as before, in which AT always change with time, A naught is constant, K is the rate constant. Of course, it is constant. As for the T, it is changes. So if we compare it with the Y equal to mx plus C, so 1 over A naught value will equal to C, K is the M, T is the X, 1 over AT is Y. Rearrange back the equation and make Y as the subject. Okay, Y as the subject. So we will get 1 over AT equal to KT plus 1 over A naught. So this is your C, M, X, Y. If we want to get the linear graph for the second order reaction, okay, we have to plot the graph of 1 over concentration versus time. Okay, if we plot a graph of the concentration versus time for the second order reaction, okay, if it is concentration A versus time, we will never get a linear graph. For the second order, if the reaction is second order, we plot a graph of the concentration versus time, we'll get a curve graph. Okay. Same goes with the first order reaction. Okay, if we plot a graph, the reaction is the first order reaction. We plot a graph of the concentration versus time of the first order reaction. We'll also get a curve graph. So that if you want to get a linear graph for the first order reaction, we have to plot a graph of ln concentration versus time. Then we will get this linear graph with the negative slope. Okay, negative gradient. Okay, as for the second order, okay, if you want to get a linear graph, we have to plot a graph of 1 over concentration versus time. Then we will get this linear graph with the positive gradient. Okay, and then for the zero order reaction, this is our initial integrated equation. AT minus A naught equal to KT, or my equation, the equation that was given by me is the A naught minus AT equal to positive KT. Okay, so we know that A naught is constant, initial concentration constant, AT, concentration A at the T time, change with time. So AT change, K constant, T also change. So we know that A naught is our C, AT is Y, K is the gradient M, and T is X. So that we rearrange back this equation to achieve Y equal to mx plus C, so that we will get this AT equal to negative K, T is the X, plus A naught is your C. So if we want to get the linear graph for the zero order reaction, okay, the reaction is zero order reaction, we just need to plot a graph of the concentration versus time. Okay, so the graph of the concentration versus time for the zero order reaction, okay, will give this linear graph, okay, with the negative gradient. Okay, so this is how we determine the order of the reaction by using graphical method. Okay, by plotting a graph and observe which one that produce a linear graph. Okay, it is concentration versus time, or it is ln concentration, or 1 over concentration versus time. Okay, so let's look at to the example that is given. Okay, this data in your textbook is in the page of 709. Okay, look at to your textbook. Okay, it is actually the reaction, the decomposition reaction of the N2O5. Okay, so the data that we have is actually the time. Okay, we have a 0 minute, okay, 10 minute, 20, 30, 40, 50, 60. This is the time of a reaction. Okay, and then the next information is the concentration of the reactant. Okay, this is the N2O5 turns to N2 plus O, O2, right? Okay, so the only reactants that we have is the nitrogen pentaoxide. Okay, look at to the concentration of the nitrogen pentoxide. Initially, at 0 minute, 0.0165 molar was introduced. After 10 minutes, it is reduced to 0.124. After 20 minutes, it is reduced to 0.093. Okay, until 60 minutes, okay, only 0.029 molar left. Okay, so these are the only information that we get from the experiment. So if let's say you want to determine what is the order for this decomposition reaction of the nitrogen pentaoxide, okay, since that we have no information about the rate, we don't change the concentration of the N2O5 in several series of the experiment, so we cannot use the first method that we have done before, rate 2 over rate 1, rate 3 over rate 2. Okay, so the only method that we can use with this data that we have time and concentration is by using graphical method. Okay, so the first step is to calculate ln for each concentration that we have here. Okay, so you have to press the calculator. Ln, the first one at 0 minute, okay, ln 0.0165. Then you will get the value negative 4.104. Then you press ln of 0.0124. From the calculator, you got the value is negative 4.4. And then you press ln 0.093. Then you will get the value negative 4.68. Okay. You press the calculator to get all the ln value until at 60 minutes. Okay, after you complete this table, and then you have to complete the table of 1 over concentration. Okay, so you have to press 1 over the first concentration 0.0165, then you will get the answer is 60.6. Ln, 1 over 0.0124, then you will get the value 80.6. 1 over 0.093, then you will get the value is 110. Complete the table. Okay, so after you have completed the table, okay, then you can start plotting your graph. There are 3 graphs that you can plot. The first graph is not, you can plot, you have to plot 3 graphs. The first one is the concentration of the N2O5 versus time. Okay, second graph is the ln concentration of the N2O5 versus time, and the third graph is the 1 over concentration of the N2O5 versus time. Okay, so you plot these 3 graphs, then look at to the output. Look at to the graph that we got. Okay, so these are the graph, okay, from the previous data. Okay, look at to the first graph. Let's analyze the first graph. This graph is the graph of the concentration versus time. Okay, so what you observe from this graph and what is the conclusion that you can make from this graph? I want Abdul Azim. Azim? What is the conclusion that you can make from the first graph, Azim?
The concentration reduces over time, and the plotted graph is a curve.
So that
So the reaction is not zero order
why the reaction is not zero order?
because it's a curve.
If it is zero order, then it's supposed to be
Uh, Zero order, it needs to be straight. Good.
okay. Good, eh?
Uh,
Yes, that's the criteria. That's how we determine the order of a reaction from the graph. Okay, if the graph of the concentration versus time is linear, then we can say that, oh, this is a zero order reaction. Okay, because from this, okay, after we rearrange the integrated equation to achieve the linear equation y equal to mx plus c, we observe that for the zero order, we plot our y is concentration A at the t time, and then the x is T, then we will achieve this y equal to mx plus c. Okay, so the graph of the concentration versus time of the zero order reaction will be linear. As for this decomposition of the N2O5, we observe that when we plot a graph of concentration versus time, it is a curved graph, so we can say that it is not a zero order reaction. And then look at to graph C. This is a graph of the 1 over concentration versus time. Okay, so when we look at the graph of 1 over concentration versus time, okay, we observe that it is not a linear graph. Okay, so 1 over concentration versus time graph will be linear if the reaction is second order reaction. When it is not linear, so that we know that this is not the second order reaction. Obviously that it is curved. And then look at to the last graph, okay, graph B. It is a graph from the ln data, ln concentration versus time. Okay, from the ln data graph, we observe that we got a linear graph. Okay, with the negative gradient. Okay, apa negative gradient? Instead of graph awak macam ni, okay, and then your graph is like this. Okay, it is a negative gradient. Okay, so when we got a linear graph with the negative gradient, so we can conclude that this reaction of the decomposition of nitrogen pentaoxide is the first order reaction. Okay, because we got a linear graph from ln versus time data. Okay, so this is how we determine the order, okay, by using graphical method. So I want you to look at to your tutorial workbook. Okay, it is the example. Okay, how to determine the order by using graphical method is in the question 13. Okay, look at to question 13 of your tutorial workbook. Okay, 13A is complete the table by using graphical method. Okay, so look at to this. It is the decomposition of the NOBR. What is given to us is the time from 0 second to 10 second and also the concentration of the NOBR. Okay, so the first step is you have to complete the table by using this data. You have to press the ln, you have to get the ln value and 1 over concentration value for each concentration that we have. Okay, and then after you got all this data, then you need to use the graph paper to plot the three graph. Okay, graph of concentration versus time, ln versus time, and 1 over concentration versus time. The same as what we have in the example just now. Okay, kena plot 3 graph. Then we check which one that will come out with the linear graph. Okay, and then from that linear graph, okay, we determine what is the order of a reaction. Then we can calculate the rate constant, okay, from the gradient of the graph. Okay, so please answer. This is your homework of the day. Please complete this. Okay, question 13 and also question 15 related to this as well. Okay, question 15, if you look at it, okay, given to us is the graph of the 1 over concentration versus time. And then, okay, look at your observation, you got linear or curve, and then determine the order of a reaction and proceed with the further question. Okay, this is the applications of what you have learned just now. Okay, so finish with the integrated rate equation. Okay, now we want to move, look at let's recap. Okay, there are 3 orders that we covered in our syllabus. Okay, 0 order, okay, when the concentration of the reactant is independent to the rate is independent to the concentration of the reactant. That is why the rate law is rate equal to K. If we have a reactant, it is A power of 0, for example. That is why rate is just equal to K. Okay, this is the unit of the rate constant. Okay, you have memorized it. Okay, half-life, we not covered in our syllabus. This is the integrated equation for the 0 order. Okay, and then we will get a straight line if we plot a graph of concentration versus time. And also the gradient of the linear graph is negative k. Okay, so if let's say you got your negative k, the gradient from graph y1 equal to y2 x1 over x1 minus x2 to the mathematical method to determine the gradient of the linear graph tu. And then you got the value is negative 20, for example. Okay, the slope is negative 20. So you should know that the k of this reaction is 20 second per second, for example. Okay, itu kalau if that is if it is the first order lah. But if it is a zero order, the K will be 20 mole per liter per second. Okay, the unit is depends on the order. Okay, so the graph of the zero order is concentration versus time. We got a linear graph. As for the first order reaction, the rate law is rate K 1 reactant power of 1. Unit of the half-life is time negative 1. Half-life is ln 2 over K or 0.693 over K. Then this is the integrated equation. Memorize it. Okay, and we will get a linear graph, a straight line when we plot a graph of ln concentration versus time with the negative K as a gradient. Okay, so this is the linear graph for the first order reaction. As for the second order reaction, the rate law will be rate equal to Ka power of 2. Okay, and the unit for the rate constant is this. Okay, half-life not covered. This is the integrated equation. And then we will get a linear graph when we plot a 1 over concentration versus time. And this is the graph. Okay,